quantum observer effect. In quantum mechanics, the act of measurement fundamentally changes what's being measured. This isn't about disturbing the system, it's more profound. Before measurement, a quantum particle exists in superposition, simultaneously occupying all possible states. The measurement doesn't reveal which state it was in. It forces the particle to choose a definite state. This is the famous observer effect, and it's been verified in countless experiments. Electrons pass through both slits in a double-slit experiment until you measure which slit they go through. Then they pass through only one slit. Photons exist in both polarization states simultaneously until measured. Then they have definite polarization. But here's what's more disturbing. Different observers can get fundamentally different results. In 2019, physicists demonstrated an experiment inspired by the Wigner's friend paradox, showing that two observers can make contradictory measurements on the same quantum system, and both are correct from their own perspectives. The experiment involved entangled photons measured by two different observers in isolated laboratories. Observer A measured their photon and got a definite result. Observer B measured a quantum property of the entire system, including A's photon and A's measurement apparatus, treating the whole thing as a quantum system still in superposition. Both measurements were valid. From A's perspective, their photon had collapsed to a definite state. From B's perspective, A's entire laboratory remained in superposition. The same physical system existed in two contradictory states simultaneously depending on who observed it. This isn't just theoretical. The experiment was performed with real photons and real measurements. The results showed that objective reality, states that exist independent of observation, doesn't exist in quantum mechanics. What's real depends on who's observing. Subsequent experiments have confirmed this, that different observers measure different properties of quantum systems, and quantum mechanics allows both measurements to be correct, despite being contradictory. Reality is observer-dependent at the quantum level, in ways that have been experimentally verified. The implications are staggering. If quantum measurements produce different results for different observers, and everything is ultimately made of quantum particles, then all measurements might be observer-dependent. Reality itself might not have definite properties until observed, and different observers might measure genuinely different realities. Some interpretations of quantum mechanics embrace this. The relational interpretation says quantum states are always relative to an observer. There's no absolute state, only states relative to who's measuring. The participatory anthropic principle suggests observers don't just measure reality, but actively participate in creating it through observation. Critics argue that macroscopic objects behave classically due to decoherence, so quantum observer effects don't apply to everyday measurements. But experiments showing observer-dependent quantum measurements raise questions about where quantum behavior ends and classical behavior begins, and whether that boundary is as clear as we assume. What's undeniable is that at the quantum level, measurements depend on the observer in fundamental ways. The measurer isn't separate from the measurement. Who observes determines what's observed. This has been proven experimentally and forms the foundation of our best theory of fundamental physics. Random number generator response to intention. For over 40 years, researchers at Princeton's Princeton Engineering Anomalies Research Laboratory conducted experiments on human consciousness affecting random number generators. They found statistically significant evidence that human intention could bias the output of electronic random number generators. The experiments were rigorously controlled. Random number generators, RNGs, produce sequences of zeros and ones through quantum processes or electronic noise, fundamentally random sources. Participants were asked to mentally intend for the RNG to produce more ones or more zeros while it ran. Over millions of trials involving hundreds of participants, the data showed small but statistically significant deviations from expected randomness in the direction participants intended. When trying for more ones, slightly more ones appeared. When trying for more zeros, slightly more zeros appeared. The effect size was tiny, only about 0.001% deviation. But across millions of trials, this produced odds against chance of billions to 1. Different participants showed different effect sizes, Some individuals consistently produced larger deviations, while others showed no effect. The same RNG would produce different results depending on who was trying to influence it. The measurement, in this case, the random number sequence, depended on the measurer. Critics have questioned the methodology, statistical analysis, and reproducibility. Some replication attempts failed, while others succeeded. Meta-analyses of all RNG studies show small but statistically significant overall effects, though debate continues about whether this represents genuine phenomena or subtle methodological issues. What's interesting is that similar effects appear in multiple contexts. The Global Consciousness Project uses RNGs worldwide and claims to detect deviations during major global events when many people's attention is focused. Individual experimenters report that RNG behavior correlates with their emotional state or intentions. More controlled studies have tried to eliminate all conventional explanations. Double-blind protocols, where neither participant nor experimenter knows the intended direction, still show effects. Automated systems without human presence during data collection still show correlations with human intention recorded before or after the RNG runs. Some researchers propose that quantum measurement involves consciousness fundamentally. If random numbers are generated by quantum processes, and quantum measurement depends on observation, then perhaps conscious intention affects which quantum outcomes manifest. The measurement depends on the measurer because consciousness collapses quantum superpositions according to intention. Mainstream physics rejects this interpretation, noting that quantum measurements don't require conscious observers. Any interaction causing decoherence will collapse superpositions. But the RNG studies suggest something more subtle, perhaps conscious intention biases which interactions occur or which measurement basis is selected. Whether genuine or artifact, the phenomenon has been documented extensively. Random number generators produce different sequences depending on who's trying to influence them. The measurement changes based on the measurer's intention, not just their procedure. If real, this suggests consciousness interacts with physical systems at the quantum level in ways we don't understand. The experimenter expectancy effect. In the 1960s, psychologist Robert Rosenthal discovered that experimenters' expectations systematically influenced their experimental results, even in studies with objective measurements. He called this the experimenter expectancy effect, and demonstrated it across multiple domains from animal behavior to human performance. In one famous study, Rosenthal told some experimenters that their rats were bred to be maize bright, and others that their rats were maize dull. In reality, all rats were genetically identical and randomly assigned, but rats labeled bright learned mazes faster than rats labeled dull, not because the rats differed, but because experimenters' expectations affected how they handled and measured the rats. The experimenters weren't consciously biasing results. They believed they were conducting objective measurements, yet somehow their expectations influenced outcomes in measurable ways. The same rat running the same maze would be measured as performing differently, depending on what the experimenter expected. Rosenthal found this effect across many domains. Teachers' expectations affected students' IQ test scores. Clinicians' expectations affected patients' treatment outcomes. Researchers' expectations affected laboratory animal performance. In each case, objective measurements produce different results depending on the measurer's beliefs about what should happen. The mechanism isn't fully understood. Some influence likely comes from subtle behavioral cues. Experimenters expecting smart rats might handle them more gently, affecting performance. But studies controlling for obvious behavioral differences still show effects. The measurement appears to change even when procedural factors are controlled. In medicine, this manifests as differences in treatment effectiveness depending on who administers the treatment. The same drug given by doctors who believe in it strongly produces better outcomes than when given by skeptical doctors, even in double-blind conditions where neither doctor nor patient knows if they're receiving drug or placebo. Studies of placebo effects show they're larger when administered by warm, confident practitioners versus cold, uncertain ones. The measurement, patient improvement, depends on who's taking the measurement, not just what treatment is given. Same condition, same treatment, different measurer, different result. Some researchers have proposed that experimenter expectancy works through quantum effects. If biological systems involve quantum processes, and quantum measurements depend on observation, then perhaps experimenters' consciousness affects which quantum outcomes manifest in the systems they're studying. Their expectations influence the physical reality they measure. Mainstream explanations focus on subtle communication, unconscious behavioral changes, and psychological effects. But studies controlling for these factors still show residual experimenter effects that are difficult to explain conventionally. Something about the measurer's mental state appears to affect what's measured. The pharmaceutical industry attempts to control this through double-blind protocols, where neither experimenter nor participant knows the treatment assignment. But meta-analyses show that even double-blind studies show patterns suggesting experimenter effects aren't completely eliminated. Perfect blinding might be impossible because the measurer's consciousness somehow affects measurements. Fundamental constant measurement discrepancies. The fine structure constant, A, is a fundamental physical constant that should have the same value regardless of who measures it. It's a dimensionless number characterizing electromagnetic force strength. Different laboratories using different methods should all measure the same value, but they don't. Different research groups using different measurement techniques have published values for A that differ by more than their stated uncertainties. The discrepancies are small, typically in the 6th or 7th decimal place, but statistically significant. The measurements are too precise for these differences to be random error. In 2018, a new measurement of A using rubidium atoms differed from the accepted value by more than 7 standard deviations. Astronomically unlikely if both measurements are correct and errors are properly estimated. Either one measurement is wrong, or A genuinely has different values in different contexts. Similar discrepancies appear for other fundamental constants. Measurements of Newton's gravitational constant G show variations between laboratories far exceeding stated uncertainties. Values published by different groups differ by amounts that should occur by chance less than once in billions of trials. The proton radius, measured by different methods, produces inconsistent results that have puzzled physicists for over a decade. Measurements using electron scattering produce one value. Measurements using muonic hydrogen produce a different value. Both experiments are rigorous and well-controlled, yet they disagree. Conventional explanations focus on unrecognized systematic errors, subtle equipment issues, or theoretical calculation mistakes that bias results. Laboratories measuring smaller values might have systematic errors pushing measurements downward, while laboratories measuring larger values have different errors pushing upward. But an alternative possibility is more disturbing. Perhaps fundamental constants genuinely have different values depending on measurement context. Not that they vary with time or space, but the different measurement procedures access different aspects of reality, producing genuinely different results. Some theories propose that fundamental constants aren't truly constant, but depend on quantum field configurations or vacuum states that differ slightly between laboratories. If different measurement setups create different local field configurations, measurements might genuinely differ. More speculatively, some researchers suggest consciousness affects measurements even of fundamental constants. If quantum measurement involves consciousness and fundamental constants are measured through quantum processes, perhaps the measurer's expectations or theoretical assumptions subtly bias which quantum outcomes manifest, affecting measured values. The discrepancies remain unexplained. Either multiple world-class laboratories are making systematic errors they can't identify despite decades of scrutiny, or fundamental constants aren't as constant as assumed. They depend on measurement context, including potentially the measure themselves. Metrology, the science of measurement, assumes that proper technique eliminates measurer dependence, but persistent discrepancies in fundamental constant measurements suggest this assumption might be wrong. The measurement changes based on who takes it, even for the most fundamental properties of physical reality. Placebo effects in double-blind studies. Placebo effects are well known. Patients improve when given inactive treatments if they believe the treatments are real. Double-blind protocols prevent this by ensuring neither patient nor practitioner knows who receives real treatment versus placebo. This should eliminate practitioner influence on outcomes. But analysis of double-blind trials reveals a puzzling pattern. Placebo effects vary by practitioner, even when the practitioner doesn't know which treatment they're administering. The same placebo given by different doctors in the same double-blind trial produces different improvement rates in patients. This shouldn't be possible. If neither doctor nor patient knows the treatment assignment, the doctor's influence should be identical for placebo and real treatment groups. Yet, patients receiving placebos from more optimistic or confident doctors show greater improvement than patients receiving placebos from pessimistic or uncertain doctors. The effect has been documented across multiple therapeutic domains. In pain trials, placebo analgesia is stronger when administered by practitioners with warmer bedside manner, even when treatment assignment is blinded. In psychiatric trials, placebo antidepressant effects correlate with the prescribing doctor's belief in the medication, even when doctors don't know which patients receive actual medication. Somehow, practitioners' beliefs and attitudes affect patient outcomes, even through the barrier of double-blinding. The measurement, patient improvement, depends on who takes the measurement, despite efforts to eliminate this dependence. Conventional explanations focus on subtle communication. Perhaps doctors who believe strongly in treatments unconsciously communicate optimism through tone, body language, or treatment instructions, affecting patients' beliefs even when specific treatment assignments are blinded. The blinding prevents knowledge of whether a specific pill is placebo, but not whether the doctor generally trusts the treatment. But studies attempting to control for these communication factors still show residual practitioner effects. Automated pill dispensing that eliminates doctor-patient contact during treatment administration reduces but doesn't eliminate practitioner effects on placebo responses. Some researchers propose quantum or electromagnetic mechanisms. If practitioner consciousness creates fields or quantum effects that influence patient biology, these influences might operate independently of verbal communication. The practitioner's mental state directly affects the patient's physical healing through mechanisms beyond known biology. Alternative medicine traditions have long claimed that the healer's intention and consciousness affect treatment outcomes. Scientific medicine dismissed this as superstition, but placebo research shows measurable practitioner effects that persist even in double-blind conditions designed to eliminate them. The implications challenge medical research methodology. If practitioner effects can't be fully controlled through blinding, then comparing treatment outcomes across studies conducted by different research teams is problematic. The measurements depend on who takes them in ways that standard controls don't eliminate. More fundamentally, if healing depends on healer consciousness even when physical treatments are identical, this suggests consciousness affects biology directly. The measurement, patient healing, is observer-dependent not just psychologically, but potentially through physical mechanisms we don't understand. Particle decay rate. Anomalies. Radioactive decay should be constant. An isotope's half-life is a fundamental property that shouldn't change based on external conditions. When you measure decay rates, you should get the same result regardless of who measures or when. But measurements of certain isotopes' decay rates show unexpected variations. Multiple studies have found that decay rates of some isotopes correlate with Earth's distance from the Sun, decreasing slightly when Earth is closer to the Sun and increasing when farther away. This shouldn't happen. Radioactive decay is a quantum process involving the strong nuclear force, which shouldn't be affected by solar radiation or gravitational variations. Yet, silicon-32 and radium-226 show decay rate variations of about 0.1% correlated with Earth-Sun distance. Even stranger, different laboratories measuring the same isotopes sometimes report different average decay rates. The variations are small and within combined uncertainties, but they're consistent. One lab consistently measures slightly higher rates, while another measures slightly lower rates over extended periods. Some researchers have found decay rate fluctuations that correlate with solar flares and solar activity. During periods of high solar activity, certain isotopes show measurably different decay rates. Other studies have found decay rate variations during solar eclipses, temporary changes in radioactive decay when the moon blocks solar radiation. Mainstream nuclear physics says this is impossible. Decay rates are determined by nuclear forces that operate at energy scales billions of times higher than solar radiation energies. No known mechanism allows solar activity to affect nuclear decay processes. Explanations for the variations focus on measurement artifacts. Perhaps temperature changes affect detector efficiency, creating apparent variations in decay rate. Perhaps electrical noise from solar activity affects detection electronics, causing false signals. Perhaps cosmic ray flux variations affect background radiation, changing apparent decay rates. But experiments controlling for these factors still show residual variations. Studies using different detector types and different shielding configurations still find correlations with solar parameters. The measurements appear to genuinely vary, not just the detection efficiency. Alternative explanations propose unknown particles or fields emitted by the sun that interact with nuclear processes. Neutrinos are abundant from the sun, and while standard neutrinos don't affect decay rates, perhaps some unknown neutrino interaction or unknown solar emission affects nuclear forces. More speculatively, if quantum measurement involves consciousness and radioactive decay is a quantum process, perhaps the measurer affects decay rates through quantum observation effects. Different laboratories with different measurement protocols and different personnel might collapse quantum superpositions differently, producing genuinely different decay rates. The anomalies remain controversial. Many physicists dismiss the variations as artifacts, but the measurements persist across multiple studies using different isotopes and different techniques. If real, they suggest that even nuclear decay, among the most fundamental processes in nature, produces measurements that depend on context and potentially on who's measuring. Rorschach test scoring variations. The Rorschach inkblot test is supposed to be an objective psychological assessment. Trained clinicians follow standardized scoring procedures to interpret patients' responses. Given identical responses, different scorers should produce identical scores. But comprehensive studies show that different Rorschach scorers produce systematically different results for the same patient responses. Even when using the standardized Exner scoring system designed to maximize objectivity, inter-rater reliability is problematic. Different clinicians score the same responses differently in ways that aren't random. Some clinicians consistently score responses as indicating more pathology, while others consistently score the same responses as healthier. The same patient responses receive different diagnoses depending on who scores them. The measurement, psychological assessment, depends on the measurer despite standardized protocols. Training and experience don't eliminate these differences. Experienced clinicians show the same scoring biases as less experienced ones. Following the scoring manual meticulously doesn't eliminate differences. Trained raters following identical procedures still produce divergent scores. More disturbing, research shows that clinicians' theoretical orientations affect their Rorschach interpretations, even when using objective scoring systems. Psychoanalytically oriented clinicians see different patterns in the same responses than cognitive behavioral clinicians. Their theoretical beliefs influence what they measure. This extends beyond Rorschach to other psychological assessments. Structured diagnostic interviews show similar scorer dependence. Clinicians using the same interview protocol with the same patient make different diagnoses based on their background, theoretical orientation, and personal characteristics. The measurement problem is fundamental. You can't directly observe mental states, only behaviors and reports. Interpretation is always required, and interpretation depends on the interpreter. Different measurers literally see different psychological realities in the same patient. Some researchers argue this invalidates psychological measurement. If measurements are interpreter-dependent, they are not objective. Others argue that psychological reality is inherently perspectival. Mental states don't have objective properties independent of the observer's framework for understanding them. Brain imaging attempts to circumvent this by measuring neural correlates of mental states objectively. But even brain imaging data requires interpretation. Deciding which activation patterns indicate which mental states involves theoretical assumptions that differ between researchers. The neural measurements themselves are objective, but what they mean psychologically depends on who interprets them. The Rorschach specifically has been criticized as unreliable due to scorer dependence. But the deeper issue extends to all psychological measurement. Internal states must be inferred from external indicators, and inference depends on the inferrer. The measurement inherently depends on who takes it, because the thing being measured can only be accessed through interpretation. Quantum delayed choice experiments. In delayed choice experiments, the measurer decides what to measure after the measured system has already interacted with the experimental apparatus. This setup reveals something deeply strange. Measurements made later in time affect what happened earlier. The classic example uses photons and a Mach-Zehnder interferometer. A photon enters the apparatus and encounters a beam splitter that sends it down two paths. The paths recombine at another beam splitter before detection. The experimenter chooses whether to insert the second beam splitter after the photon has already passed the first one. If the second beam splitter is inserted, interference occurs. The photon must have traveled both paths simultaneously as a wave. If the second beam splitter is not inserted, no interference occurs. The photon must have traveled one path only as a particle. The experimenter's choice determines the photon's past behavior. This has been verified experimentally with various systems. The experimenter's choice, made after the photon has already decided which path to take, determines which path it took. Causality appears reversed. The measurement affects the past. Different experimenters making different choices would measure different histories for the same photon. If experimenter A inserts the beam splitter and experimenter B doesn't, they measure contradictory pasts. A measures the photon as having traveled both paths. B measures it as having traveled one path. Who makes the measurement determines what happened. This isn't about information traveling backward in time. The results can't be used for communication or to change the past in ways that create paradoxes. But it does show that what happened isn't determined until measured, and different measurements determine different pasts. From a quantum perspective, the photon exists in superposition until measured. The delayed choice experiment shows that this superposition extends not just to present properties, but to past history. The past doesn't become definite until the future measurement constrains it. This implies reality is block computed rather than linearly evolved. The universe determines outcomes by considering all boundary conditions, past and future, simultaneously, finding solutions that satisfy all constraints. Different future measurements impose different constraints, determining different pasts. If true, this means measurements are radically observer-dependent. Not only do different observers measure different present properties, they measure different histories. Who takes the measurement determines not just what they observe now, but what happened in the past. Multiple observer versions of these experiments show different observers can measure contradictory pasts and both be correct from their own reference frames. Reality is fundamentally observer-relative at the quantum level. What happened depends on who observes it. This challenges the notion of objective history. We think the past is fixed and the present is where observation happens. But delayed choice experiments show the past is undetermined until future observations constrain it. The measurer's choices determine the measured system's history. Biometric sensor variations. Modern biometric sensors, measuring heart rate, blood pressure, oxygen saturation, glucose levels, and other physiological parameters, should produce objective measurements independent of who operates them. The device measures physical properties that exist regardless of the measurer, but clinical studies reveal systematic differences in measurements based on who takes them. The same patient measured by different practitioners using the same equipment produces different readings. This persists even when using automated equipment, where the measurer doesn't manually perform the measurement. Blood pressure is particularly prone to this. The same patient's blood pressure measured by different healthcare workers shows systematic variations. Some practitioners consistently measure higher values, others lower values. The white coat effect, elevated blood pressure in medical settings, varies in magnitude depending on which healthcare worker is present. This could be explained by patient anxiety varying with different practitioners. Patients might be more anxious around certain doctors, affecting their blood pressure, but studies controlling for patient anxiety still show measurer-dependent variations. The same patient in the same psychological state produces different measurements with different measurers. Glucose monitoring shows similar patterns. Continuous glucose monitors that automatically measure blood sugar should eliminate measurer dependence. The device takes measurements without human intervention. Yet patient-reported patterns differ when patients are being monitored by different healthcare providers. The measurements themselves are identical, but which measurements are noticed and recorded differs. Some researchers have investigated whether practitioner presence affects physiological states through electromagnetic fields or other physical mechanisms. Studies have measured electromagnetic fields around practitioners' hands and found variations that correlate with treatment effectiveness. Perhaps these fields directly influence patients' physiology, affecting measurements. Alternative explanations focus on subtle environmental factors. Perhaps different practitioners adjust room temperature or lighting differently, affecting physiological measurements. Perhaps the time of day when different practitioners typically see patients correlates with circadian variations in physiology. But experiments controlling for these factors still show residual measurer dependence. The same patient, same room, same time, same equipment, different measurer, different reading. Something about who takes the measurement affects what's measured. This has practical implications for medical diagnosis. If measurements depend on the measurer, comparing readings taken by different practitioners is problematic. Tracking changes in a patient's condition requires the same practitioner taking all measurements. Otherwise, changes might reflect different measures rather than changes in the patient. More fundamentally, if physiological measurements are measurer-dependent, this suggests observer effects extend beyond quantum systems to biological ones. The boundary between observer and observed is blurrier than assumed. The measurer's presence affects the measured system in ways we can't eliminate. Archaeological dating inconsistencies. Radiocarbon dating should be objective. The ratio of carbon-14 to carbon-12 in a sample determines its age through known decay rates. Different laboratories analyzing the same sample should report the same age, but interlaboratory comparison studies show systematic variations. Different labs analyzing splits of the same sample often report ages that differ by more than stated uncertainties. The variations aren't random. Some labs consistently date samples as older, while others date them as younger. In a famous 1990 study, 3 laboratories independently dated the Shroud of Turin. They received samples from the same section of cloth, processed using standardized methods, and used identical radiocarbon dating equipment. Their results should have been identical. They weren't. The 3 labs reported dates of 1260 to 1390 AD, with remarkable agreement on this range, but the detailed dates varied. One lab measured an average of 1273 AD, another 1303 AD, another 1312 AD. The differences exceeded combined measurement uncertainties. For other samples, variations are larger. The same archaeological artifact dated by multiple labs can receive age assignments differing by centuries. Some variation comes from sample contamination or inhomogeneity. Different pieces of the same object might have different ages, but comparison studies using thoroughly homogenized samples still show systematic interlaboratory differences. Different labs use different preparation methods, different equipment, and different calibration standards. But these factors are controlled and documented. When labs analyze standard samples with known ages, they produce accurate results. Yet when analyzing archaeological samples, systematic variations appear. Some researchers propose that local environmental factors affect decay rates or carbon-14 incorporation in ways not accounted for in dating models. Perhaps geomagnetic field variations, cosmic ray flux changes, or other factors create regional variations in radiocarbon ages that different labs sample differently. More speculatively, some suggest that the measurer affects measurements even in radiocarbon dating. If quantum measurement involves consciousness and carbon-14 decay is a quantum process, perhaps laboratory personnel affect measured ages through observation effects. Different labs with different theoretical expectations might measure genuinely different ages. The variations create problems for archaeology. When different labs date the same site to different time periods, which date is correct? Archaeologists typically average results or select the date matching other evidence. But this introduces subjectivity. The measurement depends on which laboratory takes it, even though it's supposed to be objective. Similar issues plague other dating methods. Thermoluminescence dating, uranium-thorium dating, and other radiometric techniques all show interlaboratory variations exceeding stated uncertainties. The measurer affects the measurement across multiple dating methods, 10 measurements that change based on who takes them. Quantum states differ for different observers. Random numbers respond to intention. Experimental results match experimenter expectations. Fundamental constants vary between laboratories. Placebos work differently depending on who administers them. Decay rates correlate with solar activity. Psychological assessments depend on the assessor. Delayed choice experiments show measurements determining past events. Biometric sensors produce different readings for different operators. Archaeological dates vary between laboratories. Science assumes objective measurement, that reality has definite properties independent of observation, and proper technique lets anyone measure those properties and get the same answer. But these cases show that assumption failing. The measurement changes based on who takes it, not from simple errors or biases, but systematically and reproducibly in ways that can't be eliminated through better technique. Quantum mechanics explicitly includes the observer. The wave function represents information rather than objective states. Different observers with different information measure different realities, and both are correct. But observer dependence extends beyond quantum systems to radioactive decay, fundamental constants, biological healing, psychological states, and archaeological ages. The measurer affects what's measured even where classical physics says they should be irrelevant. This suggests two possibilities. Either objective reality doesn't exist. Properties only become definite when observed, and different observers actualize different properties. Or objective reality exists but is inaccessible. We can only measure our observer-dependent perspectives, never the thing itself. Mainstream science treats these as technical problems solvable through better equipment. But decades of effort haven't eliminated measurer dependence. Perhaps measurement is fundamentally observer-dependent, because consciousness interacts with physical reality in ways we don't understand. The implications. If reality depends on observation, consciousness isn't passive but actively participates in creating what we measure. What we measure depends on who we are, what we believe, what we expect, and perhaps what we intend. This doesn't mean reality is arbitrary. Measurer-dependent doesn't mean imaginary. Quantum measurements are observer-dependent, but still follow quantum laws. The patterns are consistent even if observer-dependent, but it means purely objective science might be impossible. We can't step outside observation to measure reality as it is in itself. We can only measure from our perspective, and our perspective affects the measurement. 10 measurements that change based on who takes them. 10 pieces of evidence that observer and observed aren't separate. 10 hints that reality is participatory, requiring observers to become definite, and becoming different things for different observers. The question isn't whether this happens. The measurements prove it does. The question is what it means about reality and our place in it.